So let's start section 6.2. It's going to be adding and subtracting rational expressions. This will probably require practice because some students are still struggling on how to add just regular fractions. We're actually extending that concept so that we can add and subtract rational expressions. So here is really the game right here. So if P divided by Q and R divided by Q are rational expressions, then we can add them by simply adding the numerators and placing them over Q, which is our common denominator. And that's the only game we have in town in order to add, and clearly you can replace the addition sign right here with a subtraction sign and get P minus R over Q. But the only game in town is that we can only add and subtract two fractions or rational expressions when they both have the exact same denominator. So let's do something really fast. We're going to be looking at how to find a common denominator, and I'll do that for regular integers, regular fractions, before we actually start looking at rational expressions. The good thing about this is the table method I gave you to find the greatest common factor. If you watch the video, I kind of did a little bitty sideshow on how you use that exact same method to find the least common denominator, also known as the least common multiple. And that's exactly what we're going to be doing, is just the same table, just a small little bitty twist on that table gives us the least common denominator. Let's go ahead and do these examples. This is 1a. So I'm asked to add x divided by 4 to 5x plus 4. So if you'll note that our denominators are the same, they're both 4. So by the theorem above, I can write their sum by writing the division line and writing the common denominator 4, and then I just add the numerators, and x plus 5x is 6x divided by 4. And what that doesn't tell you, the theorem, is there may be some simplification. So 6, notice 6 is 2 times 3 times x over 4, which is 2 times 2. So we cancel out the 2's, and our final answer turns out to be 3x over 2. So after you add, there is always the possibility that you will need to simplify. And simplification is not an option in this class. That's a mathematical skill, and if you don't simplify, you will be counted off a few points, or a small fraction of a point maybe. If, for example, in my view, if a question were worth 5 points and you were to stop right here, depending on something like that, I might be really mean and just give you 4 out of 5 because it's so easy to simplify. There is no way I would give you anything greater than 4.5 out of 5 because it's just a piece of cake. For other questions that are a little bit more difficult to simplify, or the simplification is not obvious, I take that into account when I grade. So here, x squared over x plus 7, and I'm going to subtract from that fraction 49 over x plus 7. So we have common denominators. Our denominators in this case are not integers, but rather polynomials. That's okay, there's the same polynomial. That's all that matters. So then I just subtract x squared minus 49. And we're not done. This requires simplification. And I hope you can see that x squared minus 49 is the same thing as x squared minus 7 squared over x plus 7. And x squared minus 7 squared is x minus 7 times x plus 7. And it's being divided by x plus 7. Now here, if you need to put parentheses around it, you can. But the point is that you will see that there are two factors that need to be canceled out. The x plus 7 in the top and the x plus 7 in the bottom. And that leaves us a final answer of x minus 7. And that's our final answer. That's fully simplified. I didn't remember if I turned on the recording or not. Trust me, I have thought I was recording a lecture that was over an hour, only to finish and turns out I did not have the recording on. And that's really aggravating. So again, we have a common denominator of 3y squared. Now here is the big deal. The first thing you note is this is a subtraction. And the second thing you note is that one of the things that are going to be subtracted is not a single term, it's a sum. So you absolutely need to enclose this in parentheses. And now let's go ahead and do that subtraction. It's x minus the entire numerator, not just the x part, but the x plus 1 part. The big mistake, you can almost see it right now, the students would just write x minus x plus 1, cancel the x's, and they would have a 1 on top. And as you'll soon see, that's not going to give you the right answer. So this is equal to, on the bottom, we have 3y squared, and this is x minus x minus 1. Hold on a second, I'm going to turn off all errant sounds. Well, this is a time of the day that I get a lot of emails. So x minus x is 0. So it turns out to be minus 1 over 3y squared. And many times we write that. It doesn't really matter. It's just a choice. We have our division line, and we write the minus right in front of it, and we put 1 over 3y squared. Although this is perfectly acceptable, as would be having the negative in the denominator, but I think my math lab may be a little bit particular about that, and at any rate you should understand that these two are identical. So our next problem is we're going to have to add rational expressions that do not have a common denominator. And it's always best to add using the least common denominator. I'll give you an example. This example is particularly interesting since we use the English system of measurement. Suppose you wanted to add 1/2 plus 3/4 plus 7/8. Now you can always get a common denominator by just multiplying all of our denominators. 2 times 4, which is 8, 8 times 4, and it will be 64. But clearly the least common denominator of 2 and 4 and 8 is literally just 8. So by choosing a common denominator that is literally 64 is 8 squared, much larger than the least common denominator, that increases our work and potentially increases the amount of simplification we'll have to do at the end. So let's actually show how to find the least common denominator of 3 numbers. Let's do 12, 28, and 30. And this is going to be the table method, just like I've used before. We're going to have one column that has to do with prime factors, and then the next columns are going to have each of my numbers written as column heads. You don't know exactly how many rows to write just yet. We'll find that out here in just a second. So the first column stands for our prime factors. So this is very much like finding the greatest common factor. So LCD stands for least common denominator. The LCD is equivalent to what some other books use as the LCM. They are exactly the same thing, just a different acronym, and that stands for the least common multiple. They are identical. Don't really know why we have LCD and then someone else came along and said no, it should be LCM, or what the fight is, but it's good that you know that these two are the different names for the same thing. Different names, same thing. So what we want to do is, well, let me give myself some more room. We want to do our factor tree. Remember factor trees, it's factor 12. 12 is divisible by 2, and that gives us 6. 6 is also divisible by 2, and that's 3. So the prime factors, I know for sure that are going to occur are going to be a 2 and a 3. So remember, this is just like our other table. All I care about for at the moment is the prime factors. But I have to do this for each one of them. 28. 28 divided by 2 is 14. And 14 divided by 2 is 7. So I get another prime factor of 7. So I add that to my list. And now let's do 30. 30 divided by 2 is 15. 15 divided by 3 is 5. So I got yet another prime factor, which is 5. And it doesn't matter which order. These don't have to go to smallest to the largest. They can be there in any order. So now let's, again, just like we did before, we're going to circle at the end of our trees our prime factors. And it's also good now, just as practice, to use that to write out the prime factorization. 12 is equal to 2 times 2 times 3. So that's 2 squared times 3. 28 is 2 times 2 times 4. So that's 2 squared. 2 times 2 times 7. So that's 2 squared times 7. And 30 is equal to 2 times 3 times 5. So this is the the factor trees it's a lot to write out, and this gives you the exact same information. So let's go down with 12. How many 2's does 12 have? Has 2. How many 3's does 12 have? Just 1. It has 0 factors of 7 and 0 factors of 9. How many factors of 2 does 28 have? Has 2 of them. How many factors of 3 does 28 have? 0. How many factors of 1 does 28 have? It's 1. How many factors of 5 does 28 have? 0. Here with 30, how many factors of 2 does 30 have? 1. How many factors of 3 does it have? 1. How many factors of 7 does it have? 0. And how many factors of 5 does it have? It's 1. So here we go. The LCD of these terms, 12, 28, and 30, is equal to, you take each of the primes in your list, and the LCD is going to be each of those primes in the list raised to a power. And the thing about the LCD is the power is never 0. Never 0. So for the greatest common factor, what we did is we looked at each of these rows. So here are my factors and here are the numbers accompanying them. So we look at all of the entries in the row corresponding to my 2 factor, and for the greatest common factor I would take the smallest number. Now we're going to take the largest number. So the largest number in that row is 2. The largest number in this row is 1. The largest row in this number is 1. And the largest number in the 5 row is 1. So 2 is raised to the second power. 3 is raised to the first power. 7 is raised to the first power. And 5 is raised to the first power. So my least common denominator is 12 times 30 sorry 7 times 5 is 35. Let me get this right. So yeah, that's right. 2, let's just do it this way. 4 times 3, that's 12, times 7 times 5. So that is 12 times 35. So if we want to know what 12 times 35 is, I'm going to be lazy and literally put up my calculator here. It is 420 is my least common denominator. So if I wanted to add fractions when the denominator is 12, 28, and 30, my LCD is 420. So the thing about the difference here using this table is we take the largest number in each row. For the GCF, we took the smallest, now we take the largest, and then we take each prime and raise it to that number. So 2 raised to the second power times 3 raised to the first power times 7 raised to the first power times 5 raised to the first. So we're going to be doing something very similar to that method when we find and add fractions whose denominators are not the same. Because we cannot add them until we have denominators that are the same. So this is 2a. So all we're asked here to do is to find the LCD of the following rational expressions. So I want to find the LCD of 3x to the 5th y squared and 5x y cubed. So let's go ahead and do that using this method. So here, what I do is I'm going to have a table, prime factor column, and then a column for each of my elements, each of the terms that I'm considering. So this is going to be prime factors. And this is 3x to the 5th y squared. This is 5x y cubed. So if now the first thing we do is look at the coefficients. The coefficients, we do a factor tree. Well, 3 is prime. So 3 is prime. I don't have to do anything else. The coefficients of 5 in my factor tree, well, that's 1 and 5 because 5 is prime. So I just put 3 and then 5. What about the other things? For each variable, so notice my first term here is a product. It is a multiple of 3 factors. Those factors are 3, x to the 5th, and y squared. So all I do is x is going to be considered a prime. It can't be factored. And y is going to be considered the other prime. So that's it. Those are all of my prime factors. So now let's go. How many factors of 3 are there in this term? 3x to the 5th y squared. They're just 1. There's 0 factors of 5. X is raised to the 5th power and y is raised to the 2nd power. For 5xy cubed, there are 0 factors of 3, 1 factor of 5, 1 factor of x, and 3 factors of y. So now we want to ask the question, what is the largest number in each row? The first row 1, the second row 1, the third row 5, and the fourth row 3rd. So our LCD is 3 raised to the 1st power times 5 raised again to the 1st power, so there's my coefficient, x raised to the 5th power, and then y raised to the 3rd power, which can be simplified as 15 x to the 5th y to the 3rd. So how do I know this is a common denominator? Because it's a common denominator of 3x to the 5th y squared, 5xy cubed, because if I divide 15x to the 5th by y to the 3rd by 3x to the 5th y squared, I get a 0 remainder. And ditto if I divide it by 5xy cubed. And it's the least in the sense that the powers on the exponents are the smallest possible powers, and 15 is the smallest possible coefficient. So let's do the same thing again with there isn't another example. We're ready to go on to, well, there is another example. It's just on another page. So here is a completely different type of a question, but we're going to use the exact same procedure, except we have to factor. We have to factor. So I'm asked to find the LCD of the following terms: m squared minus 25. I hope you already can see there's an easy factorization. 2m squared minus 9m minus 5. We'll have to factor that one, and it will have a factorization. So you can see now that there's plenty of opportunities for you to strengthen your factorization skills. This last one should also be pretty easy too. So here, we're going to make our table. And probably didn't make it big enough. Let's see if I can't extend this out just a little bit more. I'm not happy. It's really, here it is in the middle of October. I have a window AC right here in front of me, and I turn it off because I'm thinking it makes too much noise. And I'm really getting hot right now. But I'll bear fit. But if you see my head breaking out in sweat, that's the reason. I'll be fine myself. I adjust to things like that really easily. So I don't know what I can do. The overhead ceiling fan got turned off. That's what it is. So again, it's better than waking up in the middle of the night and feeling like you're super hot and wondering if you've got COVID, right? I don't know how many people I've talked to whom that has happened. Not anything to mess around with. So we take each one of our expressions, m squared minus 25, and we factor it. Well, that's the difference of squared. That's the difference of squares. That's m minus 5 times m plus 5. And both of these are prime. So I'm going to put m minus 5 as a prime factor and an m plus 5 right here. And I'm actually going to express my first denominator in its factored form. M minus 5 times m plus 5. And you'll want to do that when we add these. Those are going to be plenty of examples. So the next thing we want to do is we're going to have to factor 2m squared minus 9m minus 5. And that turns out to be m minus 5 times 2m plus 1. Now I already have m minus 5 as a prime factor in my list. So the only one I have to add to the prime factor column is 2m plus 1. But I do want to put and write my second expression is m minus 5 here in its factored form. Not in this form, 2m squared minus 9m minus 5, but in its factored form. And then the final thing, we have to factor m squared minus 10m plus 25. If you think about special products, this is m minus 5 squared. So remember that m minus 5 squared is just shorthand for m minus 5 times m minus 5. And I already have m minus 5 in my list, so I'm just going to write m minus 5 squared up here. So now let's go down. In my first m squared minus 25, which in its factored form is this, how many factors of m minus 5 appear in this form? Just one. That one right there. M minus 5 is raised to the first power. M plus 5, there's 1. How many factors of 2m plus 1? Sorry, there's 0. How many factors of m minus 5 are in this term? 1. How many factors of m plus 5? 0. How many of 2m plus 1? There is 1. Down here, how many factors of m minus 5 are there in m minus 5 squared? Well, there's 2 of them. And there's not a single factor of m plus 5 or 2m plus 1. So now we're ready to write the LCD. The LCD of these terms is equal to each of my prime factors in my prime factor list, which is all of the 3 factors right here, raised to the highest number in the accompanying row. So that's going to be raised to the second power times m plus 5 raised to the first power times 2m plus 1 raised to the first power. So here is a big leave in factored form, always. So you do all of this work to factor something. You want to take full advantage of all of that work. So you leave everything in factored form, and there's no reason to write a power of 1. So you can see this is going to require a bit of practice. Okay. So this one's a good one for you. So for this one, let's see if we can't do it in our heads. Certain easy things. So when I always tell you to write down your work. And I appreciate even when it's easy that you write it down. But you may have noticed when I grade, if something can really obviously be done in your head and you don't write anything down, but you get it right, and it's something that's really obvious, I'll go ahead and give you credit for it, because it's in a stressful situation of a test. And it's so easy. The reason I require you to write things down is I have to have some assurance that you're not cheating. And I know, I want to believe none of you would ever even dream cheating, but long experience tells me that's false. And my view is, if you get a grade in the class, it has to be yours. And if I just turn a blind eye to those who are cheating, especially obviously cheating, obvious to someone like me, then it's really a slap in the face to those who do the hard work. And I simply won't have it. So that's the reason. It gives me assurances that you are doing the work and not a computer somewhere. And I hate that's, to be honest with you, I miss seeing my students on a daily basis, but I hate grading exams because I have to ask myself that question every time. And I don't like to. In the classroom, it's never an issue. Never an issue, because you won't have your cell phones out. So here we have 2 z plus 1 is prime. How do I know it's prime? It's a linear factor, and the GCF of z and 1 is just 1. What about z minus 1? It's also prime. So why do I know that? Because the GCF of z and 1 is, z and minus 1 is 1. So the LCD is going to be z plus 1. It's always going to be each of my prime factors raised to the number of times each factor appears. So it's z plus 1 times z minus 1. And you're going to get the same thing if you go ahead and you do the table. going to be a really easy table. So what is my exponents? They each appear once. So the product is always, these are my prime factors. I just call I'll call them my PFs. So it's my prime factor z plus 1 raised to the first power times z minus 1 raised to the first power, which is what I have right here. And here is extremely tempting. Do not expand this. I know you know that it's z squared minus 1. Do not, never, ever, ever leave factored. Always, even as the last step, you always leave it factored. Never undo the work of factorization. So here's a good one for you. I mean, this is going to be a long lecture. I waited till this afternoon to do it because I know it's going to be a long lecture. And I actually have it recorded from last semester when the COVID thing started. But I chose to go ahead and re-record these because, number one, I've learned a lot of things about how to record. And it never helps me. I'm talking to a new class. And I do imagine you out there and I've seen you now because I see you on Teams. So x squared minus 4, the first thing we do is we factor that. That's the same as x squared minus 2 squared, which is the difference of squares factorization. That's x minus 2 times x plus 2. So my prime factors. And my first term, I'm not going to write as x squared minus 4. I'm going to write it in its factored form as x minus 2 times x plus 2. And I just found two prime factors. Now go ahead and add them here. You can do this at any time. So that's x minus 2 and x plus 2. If you want to leave them in parentheses, that's fine. And now we have to factor 6 minus 3x. So again, it's a linear factor, but the GCF is actually equal to 3. So I'm going to factor out of 3. 6 divided by 3 is 2. Minus 3x divided by 3 is minus x. So that's how I'm going to write 6 minus 3x is the product of 3 times 2 minus x. But I get 2 minus x and 3. So 2 minus x, x minus 2. Notice this is a little bit of a trick here. I don't want to write another x minus 2 and a 2 minus x. That's going to be a mess. So I want to change and note that 2 minus x is the same thing as minus x minus 2. So I'm literally going to write this as minus 3 times x minus 2. So what I'll do here is I'm going to write my minus 3 right there. I'm going to keep the minus on that part right there, and that's all I have to do. I know normally our greatest common, we're not talking about greatest common factors, we're talking about least common factors now. And I'm just going to attach the minus on, what I wrote here is not right, is equal to minus 3, no, yeah it was, sorry, I'm not looking, times I didn't notice that I'd actually already switched the order. So it's equal to minus 3 times x minus 2. So another prime factor is going to be minus 3. Now if you wanted, you could literally write a prime factor is minus 1 and then 3, but that's too much. So now we're ready to go ahead and fill out our table over here. There is one factor of x minus 2. There's one factor of x plus 2 and 0 factors of minus 3. Here I need to rewrite this as minus 3 times x minus 2, because that's what I changed it to. There is 1 x minus 2's, there's 0 x plus 2's, and there's 1 minus 3. So again, we want to record the total, the largest number we encounter in each row. And the largest number, every row is going to have this column of numbers right here. The smallest number is always going to be 1. You're never going to have zeros. We had zeros when we were looking for the GCF, but here we're never going to have zeros. Every number we have in this part is always going to be greater than or equal to 1. So let's go. So this is equal to minus 3 raised to the first power times x plus 2 raised to the first power times x minus 2 raised to the first power. So don't forget the negative right there. So here we go. So I have this really involved formula for adding or subtracting rational expressions. But before we do that, I want to show you something different. And I'll try to show you, this really works really, really well. But I'm going to show you one way. I'll concentrate on this way. This looks really, really, really nasty. And you explain, and you explain, and you explain, and students still don't get it. So I literally wrote up this algorithm. Find the LCD first. Let K be our LCD. Then for each denominator, so you just label your denominators, D1, D2, D3. Find the related value of K1, K2, K3 by this formula. Then I just take each of the numerators and multiply them by K1. Take the next numerator, multiply it by K2. Next numerator, multiply it by K3. And it's all over LCD and you're done. It looks really nasty. It's not. But I do want to show you another method, especially for those of you who may be in this class who took developmental math. So, and this is especially all the way down in developmental math 0018. That's the lowest level of developmental math that we offer at Eastern Florida State College. So let's add 1/2 plus 3/16. So let's find our LCD. Well, 2 is prime, and 16 divided by 2 is 8, divided by 2 is 4, divided by 2 divided by 2. So 16 is equal to 2 times 2 times 2 times 2 is 2 to the 4th. So our primes are just going to be 2. That's it. 2 and 16. Well, we have one factor of 2 and 2 and 4 factors here for 16, so my LCD of 2 and 16 is equal to 2 raised to, what's my largest number? The fourth, so that's 16. So here is how we would proceed. It's called vertical addition. And I will do at least one problem using vertical addition of fractions. We write 1/2 plus 3/16. But 3/16, I'm going to convert each one of these 1/2 and 3/16 into a fraction with my LCD of 16. So clearly 3/16 is equal to 3/16, and that's going to be 16. So the fractions over here are each going to have my LCD written. Another way, I know that's going to be a 3 because I didn't change anything. 3/16 has to be 3/16. I can't change anything. But up here, this is what we do. 16 divided by 2 is 8. 8 times 1 is 8. And then what you do is we add them. Our final result is going to be over our LCD, and we add our top numerator and our bottom numerator. Why do we add them? Because that's what it tells us to do right here. So we get 11/16. This is called vertical addition. We're going to be doing pretty much the same thing, except writing things vertically takes up a lot of space, and our paper is kind of made so that we write left to right. So that's pretty much what we're going to be doing. So I'm going to show you exactly what we're going to do. So let's talk you through that. So first we're going to find the LCD, very first thing. And then I'm going to label each of our denominators as first denominator, second denominator, third denominator, however many it is. And then I'm going to find the k values. So my first k value is given by the LCD, which is my k without a subscript, is the LCD divided by my denominator 1, or just k divided by d1. Then I find my k2 value. My k2 value is again my LCD divided by my second denominator. That's exactly what I did here. This is my LCD, and this is my first denominator. My LCD divided by my first denominator is 8. So my k1 value would be 8, and then I'm multiplying 8 times my numerator there. Here 16 divided by 16 is my k2 value, which is 1. 16 divided by 16 is 1. And then 1 times 3 is 3, and I added them up. So literally what I've done is I've taken what I did right here, broke it up into little steps, labeled some things with variables, and I've written down the procedure. So let's do one. I don't know why. Okay. So this is the whole thing. I'm saying, why am I asking you to do that? So what our goal is to add 2 over 2x squared y plus 5 over 3xy squared. So we're not going to do b. We're just going to do 2x squared y, 3xy squared. We're just going to do a. And what I find in a, I'm going to use to solve, to add. We're not solving for anything, but to add these two rational expressions. So here we go. So we want to find the LCD, and when they're rational expressions like this, it's really easy. We don't have to make a table. The LCD of 3xy squared times 2x squared y. Well, the prime factors I have a 3, I have a 2, I have an x, and I have a y. Now I just simply write 3xy squared and 2x squared y. How many factors of 3? 1. How many factors of 0 in my first term? How many factors of 2 in my first term? 0. How many factors of x in my first term? 1. How many factors of y in my first term? 2. How many factors of 3 in my second term? 0. How many factors of 2? 1. How many factors of x? 2. How many factors of y? Just 1. And if you want, you can just circle the largest number. So my LCD is equal to, let's do our coefficients first, 3 to the first power times 2 to the first power times x to the second power times y to the second power. So my LCD is 6x squared y squared. So let's use that to add. We want to add 2 over 2x squared y plus 5 over 3xy squared. So by my formula, you can fill out part of the answer. Of course, there's going to be simplifications. So I just found the LCD of the denominators. Here it is right here. So the sum is always going to be over the LCD. And then it's going to be 2 times K1 plus 5 times K2. So I have to find these K1 and K2 values. Well, by the formula, K1 is equal to my LCD divided by my first numerator, which is 2. So my LCD is 6x squared y squared divided by, it's not divided by my numerator, sorry. It's divided by my first denominator. There we go. So it's 2x squared y. It's my LCD, for Christ's sakes. X squared y squared. Now we're going over my first denominator, 2x squared y. Well, 2 divided by 6 is 3. X squared divided by x squared is 1. Y squared divided by y is y. So K1 is equal to 3y. K2 is equal to, again, my LCD divided by my second denominator, which is 3xy squared. Well, 6 divided by 3 is 2. X squared divided by x is x. Y squared divided by y squared is 1. So that's my K2 value. So let's go ahead and replace my K2 values with what I have written down here. So that's going to be 2, my K1 and my K2 values. So it's going to be 2 times 3y, 5 times 2x. Now I've got to simplify. So to simplify, I need some more room. So this is what I'm going to do. We know how to do that, so I'm going to erase all of this. And it's kind of nice, you know, I will actually be using this method to project on the board when I teach back in class. I'm actually taking my laptop and you'll be seeing a projection of my digital whiteboard here. So 2 times 3y is 6y. 5 times 2x is 10x over 6x squared y squared. Now, I'm hoping you're seeing that we're not quite done with this yet. Because we can factor, we can simplify the numerator. The GCF of these two terms is going to be 2. You can factor out at 2. 6y divided by 2 leaves me 3y. 10x divided by 2 leaves me 5x. Over 6x squared y squared. And then finally, I can do one last simplification. 2 divided by 6 is 1/3. So the 2 becomes a 1. So that's 1 times 3y plus 5x, which is 3y plus 5x. And the 6 becomes a 3. And that is our answer. Did I do something wrong? Two x squared y. Okay, you know, I did something. I'm fine. On my sheet of paper, my cheat sheet, what I did before, I don't have 2x squared y. I just have x squared y, and hence I have a different answer. And then I have 3x cubed y for, is that what it is? Yeah, no, I changed it. Yeah, that's what I did. So what I actually did is, this is fine. Everything I did is fine. What I have in my notes over here is exactly what your book has for 4A. But what I wanted to do is to use what we got from doing 3A to add 4A. So I changed 4A, and I think I also changed slightly 3A to make that work. So what you have in the book may very well differ from what I just did for those two accompanying questions. Don't need to see that. Well, I just close it out. Let's do another one. Yeah, it's involved. Students literally hate this part of the class. It's important that you get it, though. It's an important skill. Very seldom in math are we so blessed that we never have to deal with fractions. And this is not an example. And when we do deal with fractions, that they're just numerical fractions without variables. Yeah. And if you're thinking, well, the math you have in your life, you will never do that. You're right. That's probably right. Unless you're going into STEM sciences, STEM or sciences or technology or engineering. So we have to find the LCD of x plus 2 and x minus 2. Now I'm going to challenge you to confirm that it's just simply x plus 2 times x minus 2. And what we want to do is we want to add, let me write this down here. We want to add 3 over x plus 2 plus 2x over x minus 2. So that's equal to our LCD, which I just found and told you to verify, and I know it's going to be 3 times k1 plus 2x times k2. And of course all of that is on in my numerator. So I have to find what k1 is and k2 is. So let's do that. k1 is my LCD, and you always leave it in factored form. Make that look more. And I divide it by my first denominator, x plus 1. So k1 represents the first term, first denominator. I'm talking x plus 2. So the x plus 2 and the x plus 2 cancels. So k1 is equal to x minus 2. My k2 term, again, is going to be my LCD that I found, x plus 2 times x minus 1 over my second denominator, x minus 2, and those two terms cancel, so it's x plus 2. So the end result is going to be 3 times k1, which is x minus 2, it needs to be in parentheses, plus 2 times x times k2, which is x plus 2, all over my common denominator. Get some more space here. So the only thing we have to do is expand and simplify the numerator. So that's 3 times x times 3 times minus 2 is minus 6. 2 times x is 2x squared. 2x times 2 is 4x. All over my LCD. I'm just going to do, if you want, you can just write LCD here, and then at the very, very last step, you write in your actual LCD. It's kind of nice, because otherwise you're just copying the LCD over a million times. So we have to simplify this. So that's 2x squared, 3x plus 4x is 7x minus 6, and it's all over my LCD of x minus 2 times x plus 2. Do not ever multiply it out. Leave it always in the factored form. Now ideally you would have to check to see if the top factors is 2x squared plus 7x minus 6, can that be factored? And the good news is I don't think seldom is the numerator a polynomial? Here it is. That is, here's the keyword, not prime. That means you don't have to worry about factoring it. I don't think I found a single one. When I did all of these exercises, I thought, oh, after all of this, I have to go and see if this is factored, and if it can be factored, I have to cancel out. And I don't think I found a single one where you had to do that. And that's probably not by, that's just how things turn out. There's a theorem that was recently proved just a few years ago on the set of polynomials that could be factored. And it's a really, out of all of the total polynomials, those that can actually be factored, in math we call it a set of measure 0. Well, first just imagine that all the polynomials is infinite in size. It's an infinity that you can't even understand. And the set of polynomials out of that infinity that can be factored is so different in magnitude that you can consider it as just being equivalent to 0. Now, that's just by analogy. So what are we going to do with this one? We almost have a common denominator. So can I factor out a negative from 1 minus x? Let's do that. So I take my negative, put it in front of parentheses, 1 becomes minus 1, and x becomes plus x. And then we write it in standard form with the negative there. Oh wow, so if I write this as 2x minus 6 over x minus 1 minus 4 over minus x minus 1, this one's not going to be so bad. That's the same as 2x minus 6 over x minus 1. Minus a minus is plus 4 over x minus 1. Now all we need to do is, I think it's good right now to come over here and nothing. It's not a good idea. I take it back. We have a common denominator. By just factoring out a minus 1, I found a common denominator. And now I'm adding suddenly. Makes it easier. So it's 2x minus 6 plus 4. So that's equal to 2x minus 2 over x minus 1. I do have to simplify. In this case, the numerator is an easy factorization. I can factor out a 2. That's the only type of factorization that I've ever found in these, is the easy GCF type of factorization. And here, if you need to put the denominator in parentheses to see that now the numerator and the denominator cancel, and my final answer is just plain 2. That's all there is to it. So, let's do another one. Yeah, this is the time you spend on your homework is going to really increase. I'm just giving you a warning right now. So we're going to subtract these two polynomials. So sorry, to subtract, they're not polynomials at all. Subtract these two rational expressions. So the first thing we have to do is we have to find the LCD of k squared minus 4 and k squared plus k minus 2. I'm going to go ahead and maximize that window, and I'll come back to it. So to find the LCD, we have to factor those. So I'm hoping you realize 4 is 2 squared, so that's k minus 2 times k plus 2. And k squared plus k minus 2. See if you can do that in your head, the factorization. It's a polynomial in k is equal to k minus 1, k plus 2. So we can make our little table. We might as well do that. We now know what our prime factors are going to be. I'll just call my prime factors PS. K minus 2. And if you want to keep them in parentheses, you can. It doesn't change anything. K plus 2. Sometimes it helps to pattern match. And k minus 1. And the rest is going to be pretty simple. We only have two terms, and we're going to write them as in their factored form. That's always important if you're going to use this method. K minus 2, k plus 2. Now if you all are already good at finding the least common denominators of rational expressions, and you have to find the least common denominator, not just a common denominator, and you feel comfortable with that, you can do it that way. That's fine. So I don't know a better way. I literally developed this method. This table method right here was developed to find the least common multiple, the least common denominator, and then I just extended it to find the greatest common factor. I don't know any book that uses this table method, but to me it seems natural, and it's something I developed on my own, so it's even more natural for me, so I'm sending it to you. So how many factors of k minus 2 are in my first denominator? Just 1. There's 1 factor of k plus 2, and there's 0 factors of k minus 1. How many factors of k minus 2 in the second denominator? 0. There's 1 factor of k plus 2 and 1 factor of k minus 1. So just circle the largest number. So the LCD is equal to, remember I'm doing my prime factors, k minus 2 raised to the first power to the k plus 2 raised to the first power to the k minus 1. So that's my LCD. That's going to be important. So we want to use it to do the following. We want, where is it? We want to find 5k over k squared minus 4 minus 2 over k squared plus k minus 2. So I already know that the answer is going to be over my LCD. So I'm just going to write the LCD, and I'll replace it with all of this up here at the very end. And it's going to be my first numerator, 5k, times some k1 value, minus 2 times some k2 value. I'm writing my k kind of weird right there because the variable over here is k, and that just by coincidence happens to be the same letter that I use for my k1 and k2 factors. So my k1 factor is found by my LCD divided by my first denominator. So that's going to be k minus 2, k plus 2, k minus 1. And my denominator I should get from this list up here. You can either write the factorization underneath of it, but you write it in its factored form always. So k1, if you can see, you should be able to see k minus 2, those factors cancel, k plus 2. So my k1 value is just k minus 1. Myself a little bit more room. My k2, again, is my LCD divided by my second denominator. I'm writing all this out. I'm sure when you do it, you'll figure out a better way than to write all this out each time. One way of which is just to do it in your head. And my second denominator, I don't want to write divided by k squared plus k minus 2. I want to write it in my factored form. Always. Once you've factored it out, never go back to the factored form. Indeed, when I wrote this right here, I should have replaced k squared minus 4 with its factored form, or k squared plus k minus 2 in its factored form, but I wanted to bring it over exactly as it was given to us in its text, in the text. So there's a k plus 2 factor that cancels, and a k minus 1 factor that cancels. So let's go down here and let's transfer this down. I have 5k times my k1 value. My k1 value is equal to k minus 1 minus 2 times my k2 value. The only thing left up here is k minus 2. All over my LCD. Now you see why I'm just writing LCD down, because I've got a ways to simplify. So 5k times k minus 1 is 5k squared minus 5k minus 2 times k is minus 2k. Minus 2 times minus 2 is plus 4. All over my LCD. So the only thing I have to do now is simplify my top part. 5k squared. 5k squared stands alone. There are no degree 2 terms. Minus 5k minus 2k is minus 7k. Then I have plus 4. All of this is over my LCD, which is k minus 1, k plus 2 times k minus 2. And we're done. We're going to do one more example, and I'm going to call it quits. We will do maybe 6 and 7. And this is, again, it's hard to get through this in a single setting in class. And this is a very important procedure, and we don't get through it in a single setting. I actually have 2 class periods dedicated to 6.2. But I'm doing it all in one lecture. But I do feel justified in skipping an example, because if you want to see those examples worked out, you crack open your e-textbook and watch and see how they do it. You'll see they have a different procedure altogether. So we want to, the very first step, we want to find the LCD of 2 x squared minus 9x minus 5 and 6x squared minus x minus 2. So that means we have to factor each one of these. So the factorization skills are really important, that you get these and you get them really, really well. So it looks like I'm going to have to factor these myself. That'll be fine. I don't have this particular one done. In my notes, apparently this is the one I give up on in class because we run out of time. So we'll actually factor these together, as I have to do the factorization. And as I said, when I do the factorization, I use the very exact method that I taught you. That's the reason I taught you that method. So I have a 2x squared. I don't want to use that color. 2x squared minus 5 and minus 9x. So this is going to be 2x and x. That's going to be minus 5, and that's going to be plus 1. So 2x times minus 5 is minus 10x, and x times, in case you're wondering, there is no sign there, that's just a plus. That's plus x. And minus 10x plus x is minus 9x. So my factorization, remember we go kitty corner, 2x plus 1 times x minus 5. So let's do the same thing for the next polynomial. And all of these, none of these are prime. They choose these so that none of them are prime. Okay, I got it. So this is going to be 6x squared minus 2 and minus x. So it's going to give me minus 4x and plus 3x gives me minus x. So my factorization here is going to be 2x plus 1 times 3x minus 2. So now I'm going to find the LCD. So a lot of steps. Part of it isn't so bad. Part of it is our prime factors. At this point, I have a 2x plus 1, and then I have an x minus 5. Oh, and then I have a 3. That's 2x plus 1 I already have on my list. This is 3x minus 2. So I have three prime factors, so that's not so bad. And I'm going to call this is my denominator 1. I don't want to write all of this stuff down here, but I'm going to call this my denominator 2. So I'll just refer back to these. So how many factors of 2x plus 1 are in my denominator 1? There's one factor. How many factors of x minus 5? There's 1. How many factors of 3x minus 2? There's 0. Denominator 2. There's one factor of 2x plus 1. there's 0 factors of x minus 5 and 1 factor of 3x minus 2. So the LCD, notice each factor only appears once. 1 is the largest number in each list. So my LCD is 2x plus 1. So always grab the primes here, times x minus 5 times 3x minus 2. So let's add. We wanted to add 2x minus 1 over 2x squared minus 9x minus 5, which we factored is 2x plus 1 times x minus 5. Are we adding? Yes, we're adding. And then I'm going to add that to x plus 3 over my second denominator, which is 2x plus 1 times 3x minus 2. So I've got everything that we need right here. That's what we're doing. Change color. So I know this is equal to something over my LCD. And right here my LCD is. So it's my first numerator, 2x minus 1, times something I'm calling my K1 value. Then plus my second numerator times something I'm calling my K2 value, all over my LCD. So let's find my K1 value. My K1 value is equal to my LCD divided by my denominator 1, which is 2x plus 5. I'll go ahead and write it here. 2x plus 1, x minus 5, 3x minus 2. If you all have made it this far in the lecture in one sitting, you are A students. I know that attention deficit disorder is hard, is a problem with younger generations. And I realize that you probably have already paused it. So let's cancel out the factors. So K1 is equal to 3x minus 2. My K2 value is my LCD. This is going to be the last one we do today. And if you have questions about one that I've not done, you just email me and I'll sit down and I'll work it out for you and send it to you as a PDF. And my second denominator is right there, 2x plus 1. That's the reason it's kind of nice to write them in their factored form, 3x minus 2. And then we just cancel like factors. 3x minus 2 cancels, 2x plus 1 cancels, so it's equal to x minus 5. So we're ready to go. So I have found my values of K1 and K2. So it's equal to 2x minus 1 times K1, which is 3x minus 2, plus x plus 3. That's supposed to be a plus there. I can do a better job than that. Times x minus 5, which is my K2 value. What I just figured out. all of this is over my LCD. So now you see why I don't write LCD until the very last step. So now you have to FOIL these. So 2x times 3x is 6x squared. 2x times minus 2 is minus 4x. Minus 1 times 3x is minus 3x. And minus 1 times minus 2 is plus 2. And I'm adding, all of this is over one big, huge, long division line, right? X times x is x squared. X times minus 5 is minus 5x. 3 times x is 3x. And 3 times minus 5 is minus 15. I'm still not ready to write that LCD down there, because there's going to be a lot of simplification. So let's simplify. 6x squared plus x squared is 7x squared. Minus 4x minus 3x is minus 7x. Minus 5x is minus 12x. Plus 3x is minus 9x. Plus 2 minus 15 is minus 13. And this is all over my LCD. What was my LCD? I'm not going to write it down. I'll just scroll up so you can see what it was. All over this right here. This was my LCD. 2x plus 1, x minus 5, 3x minus 2. And of course this is assuming that I did everything right in my head up here. I have not worked this one out. I didn't see anything wrong. If you see anything wrong, feel free to email me and I will make the correction. Whew, what a long lecture. Students always find this part not so conceptually difficult, but there's a lot of those steps there, and you have to put them all together right. So the only advice I have is to practice a lot. And that's how you're going to get it.